Hello students, welcome to EPG Pathshala. I am Dr. Shruti Thakur from University of Delhi. Today we are going to discuss about the module Physical Properties of Stars from paper Astronomy and Astrophysics. After studying this module, you shall be able to understand that the distances of celestial objects are very large and special methods are required to measure them. You should be able to learn that parallax is the shift in the position of an object when viewed from different locations. You will also appreciate that annual parallaxes of stars are very small and therefore the parallax method can be used only for neighborhood stars. You will also understand that measuring parallaxes is a complicated process and only a few observatories specialize in it. You will learn that the motion of stars perpendicular to its line of sight is called the proper motion of the star. You will also understand that the proper motion changes the coordinates of a star. So far we have managed to fix the direction of a star in terms of two angular coordinates. Refer to the horizon system, the equatorial system, the ecliptic system and the galactic system of coordinates in module 1, 2 and 3. We now embark on the study of physical characteristics of stars. These characteristics include the luminosity of a star, its effective temperature, its spectra, sources of its energy, state of its evolution. Critical to such studies is the astronomical data such as the distance of a star, its motion in the sky and its brightness. Therefore, in this module we turn our attention first to the distances of stars. Then we shall take up their motion in the sky. Remember that the coordinates of a star only fix its direction. For a complete location of the star in space, we also need its distance. As we shall see below, the distance of a star also fixes its luminosity, spectral class, and other characteristics. Since distances of a celestial object are very large, even the distance of the Sun is 1.5 into 10 to the power 11 meters. Therefore, special methods and techniques are required to measure them. The units required are also special. The distance to the Sun is called as astronomical unit. Distances of members of the solar system are measured in astronomical unit. For stars, even astronomical unit is too small. Light year, which is 9.46 into 10 raised to the power 15 meters, is a very popular and descriptive unit. However, most suitable unit for astronomers in many respects is a parsec, which we shall define in next few pages. Parallax is the apparent shift in the position of an object with respect to the background. When seen from two different positions A and B, the direction of star changes with respect to the background. As seen from point A, the star appears to be in the direction AX. As seen from B, the star appears to be in the direction of BY. The change in the direction of star with respect to background, that is the angle ASB, is the measure of parallax of a star. This angle is measured in radians. One can convert degrees to radian from the fact that pi radians is equal to 180 degree. Parallax is measured in terms of the angular changes in direction. Greater the baseline, which is shown as AB in the picture, so therefore the greater the baseline, bigger is the parallax angle. For same baseline, the far away stars have smaller angle of parallax as compared to the nearby stars. The stellar distances are so large that the angular change in their direction is extremely small unless the baseline AB is long. Therefore, we look for long baseline so that the angles are measurable. The longest baseline available to the observers on Earth is the diameter of Earth's orbit around the Sun, which is shown in the picture. Even with this baseline, the parallax angles can be measured with difficulty. Observations are made from E1 and after 6 months from E2. E1 and E2 are the opposite ends of Earth's orbit. Angle E1S E2 is the change in the direction of the star S. Half of this angle is represented as P is called the parallax or the annual parallax of the object S. The angles are small, they can be expressed in seconds. We generally represent angles in degrees, but 1 degree has 60 minutes and 1 minute has 60 seconds. So one can imagine that how small the angles are that we are measuring it in terms of seconds. Even for the nearest stars, these angles are only a fraction of arc seconds. The distance of Sun from Earth is 1.5 into 10 to power 11 meters. This distance is called as astronomical unit, denoted by capital AU. With the baseline of Earth's orbit around Sun, if the parallax angle of a star is 1 second, then the distance of the star from Sun is called as 1 parsec. The distance of star is proportional to the inverse of parallax angle. This implies the smaller the angle, larger is the distance. Angle is measured in arc second and distance is measured in parsec. Why do we lay so much importance on accurate measurement of distances of stars? The fact is that if we wish to know accurately the physical properties of stars and their objects and other objects, properties such as luminosity, effective temperature, chemical composition in order to understand their origin and evolution, the accurate knowledge of their distances is of paramount importance. Historically, the discovery of stellar parallaxes provided another argument against the geocentric universe, which held the Earth to be at rest and the center of the universe. The arguments of Copernicus and Galileo disfavoring the Earth as the center of the universe were not accepted because their critics pointed out that if Earth really revolved around the Sun, one must observe the parallactic motion of stars. At that time, such an observation was not possible because of lack of suitable instruments. However, the successful observations of stellar parallax in 1853 by F. Bessel vindicated Copernicus and Galileo and dealt a severe blow to the geocentric universe. For distant objects in the galaxy and outside, there are several indirect methods which we shall describe in due course. However, all these methods depend critically on the distances of the nearby stars measured by the method of annual parallaxes. In that lies the importance of the accurate measurement of parallaxes by satellites. So now let us see the complexities in the measurement of parallax. Our baseline is the Earth's orbit around the Sun, which is called ecliptic. The picture shows the parallactic curve is generally not a simple one. When the star S is in the direction of ecliptic poles, we see the star execute a circle as we move in the orbit around the Sun. If the star is in any other direction, the parallactic curve is an ellipse. Only when the star is in the plane of the ecliptic is the parallactic motion a straight line, as you can see from the picture. Stars are moving. The star's own motion is added to the parallactic motion. The combined motion becomes quite complicated. Observers have to extract the parallactic motion from this complicated motion, which is a difficult task. The method of parallax serves to measure distances of only nearby stars, for example, stars at a distance of 100 parsec from the Sun. This distance has a parallax angle of 0.0 arc seconds. For faraway stars, parallax becomes even smaller and the errors in the measurement becomes comparable to the parallax themselves, and hence the uncertainties in measurements become too large to be acceptable. European satellite Hipparchus has measured parallaxes of stars which are not accessible from ground. The accuracy of this instrument is much better as compared to the ground-based instrument. Ground-based observations can measure the distance of star up to 100 parsec, whereas Hipparchus could measure accurately the distance up to 1000 parsec. This table shows the coordinates which are taken at the epoch of J 2000, that is the January 2000, and the distance of different stars. The parallax is measured in milli-arcseconds. The right ascension of Proxima Centauri is 14 hours 29 minutes 43 seconds and its declination is minus 62 degrees 4 minutes 46 seconds. Parallax measured in milli-arcseconds is 768.87 and its distance is 1.30 arcsecond. Alpha Centauri E, another star, has a right ascension of 14 hours 39 minutes 36.5. Its declination is minus 60 degrees 50 minutes and 2 seconds. Its parallax measured in milli-arcsecond is 747.23 and its distance is 1.33, and so on. So we can clearly see that stars are very far away from us. Like everything else in universe, the stars are also always in motion. They appear fixed because they are very far off and the change in their direction is so small that it cannot be appreciated by naked eyes. In this section, we will study the motion of stars. The picture here shows the star and the observer at O. The straight line from observer to a star is called the line of sight, which is shown as OS in the picture. The star is also moving in some direction. It has some velocity. The velocity vector of a star can be broken down into two components. One component is in the direction of line of sight. This is called as the radial motion of the star. The other component, which is perpendicular to line of sight, is called as the proper motion of star. The proper motion of star in this picture is denoted by Greek letter mu. Proper motion is measured in terms of angle. This is a small angle measured in arc seconds per year. It is obvious that the motion of a star will bring about a change in its coordinates. In this picture, a star moves from position x to position x prime. The right ascension and declination of x are shown as alpha and delta respectively. Now the position of star has changed from x to x prime due to its motion. The right ascension has changed as the star now lies on a different meridian. The declination has also changed, that is, the star is not at the same arc length from equator as before. Its new declination is represented as delta plus d delta, where d delta is a small change in its declination. As the star x moves to x prime due to proper motion in 1 year, its right ascension changes by mu alpha while its declination changes by mu delta. Considering the triangle shown in red, we get mu cos phi equal to mu delta and mu sin phi equal to cos delta times mu alpha. These equations help us to calculate changes in equatorial coordinates of a star due to its proper motion. The proper motion then can be expressed as mu alpha square plus mu delta square whole square root. The rate of change in the position of a star is very slow. It is not appreciable in 1 year or even in a decade. If a photograph of a small region of sky is taken for an interval of 10 years, some stars are seen to have moved slightly against the background objects, which do not change their positions. We need photographs for several decades apart of the region of the sky which contain the star whose proper motion is to be determined. A and B are the sketches of such photographs. In this interval of time, the star has moved from x to x prime. Notice the background remains the same. The proper motion of the star is found from the displacement x prime, which can be obtained by the superposition of these photographs. Knowing the displacement and time elapsed between the two photographs, the proper motion can be calculated. It is obvious that the accuracy of the measurement of proper motion can be increased by selecting photographs separated by long intervals. However, much of the advantage is offset by the errors in the position measurement at earlier epochs. Measurement of the proper motion of a star is not as simple as it appears. It is obtained by analyzing the complicated path that the star describes in the sky due to the combination of proper motion and the parallactic motion. Hipparchus has also measured the proper motion of large number of stars. It is also important that the position measurement at two epochs be referred to the same equator and equinoxes, so that change in the coordinates caused by Earth precession can be avoided. We can locate stars that are probably near by looking at their proper motions. For example, for stars with large proper motion has a very high probability that it is very near. Proper motion of a star gives us statistical clues to its distance. If a star is seen with a small proper motion, it is most likely that it's a distant star. But we cannot be absolutely certain, since it is possible that it is a nearby star moving directly away or towards us in the direction of line of sight. The sun itself is also not stationary. The velocity vector of a star then must be corrected by subtracting from it the velocity vector of the sun. The corrected motion of a star is termed as peculiar velocity of the star. Peculiar velocities of stars are essentially random, and their typical magnitude is such that in a time of 1 million years, the shape of the present constellation may change completely. Hipparchus also measured the proper motion of stars. The figure is taken from the Introduction to the Millennium Stars Atlas and was produced by Denis Ticiccio for Sky Publishing Corporation. Note that the proper motion of the star stands out clearly as the movement of the star against the background stars with time. Denis Ticiccio observations were so accurate that the effect of the parallax of the star is also evident in the picture. It is seen as the wavy motion of the star. The individual observations are also shown in black circles with relevant observational dates. About its linear motion, this wavy motion has a period of 1 year corresponding to the Earth's orbital motion around the Sun. So students, let us summarize what we have learned in this module. The stellar distances are essential for fixing physical properties of stars, such as their luminosity. Distances of nearby stars are determined by the method of parallax. Observations are made from the two ends of Earth's orbit around the Sun. Half the angular displacement in direction observed from these points is called the annual parallax of a star. If the annual parallax is 1 arcsecond, the distance is said to be 1 parsec. Generally, the reciprocal of parsec in arcseconds is the distance in parsec. The motion of a star perpendicular to its line of sight is called the proper motion of the star. Proper motion changes the equatorial coordinates of the star. Therefore, proper motion is given in terms of its component changes in right ascension and declination. Proper motion is a small quantity. It is measured in arcsecond per year or milli arcsecond per year. Thank you.